when they read and write from it, they have to specify a ID for the file, and then you actually look up which buffer they're going to pull from based on that. It would be complicated and pointless. So the keyboards. We have this one here. I've been talking about the difference between PCMCIA and USB keyboards a number of times. PCMCIA is wrong. PS2 is right. PCMCIA is those cards that you put into laptops. You know, if you look at your laptop on the side of it, you'll see a great big slot about this wide and about this high. And you can take like a network card or something and put it into your laptop. You might have to use your older laptop from a decade or two ago, but that's what a PCMCIA slot is. I haven't seen one in years on a new laptop anyway. Yours is huge.
Mine's old enough. Well, it only seems huge because I bought this massive 12-cell battery.
Yeah, you don't have a PCMCIA slot though.
I don't know.
Oh, what is the top thing? That's a PCMCIA. You're right, you do have one. Never mind. He's got one. Somebody still has one.
It's a dinosaur.
I have one too on my laptop. I actually have two of them.
I just have an SD card slot on mine.
Yeah. Yeah, it used to be popular. Okay, anyway, so back to the point though. PS2 is the interface that older keyboards used, and USB is the new one. And we wrote an interrupt handler that would figure out the rate of pushing buttons on the PS2 keyboard, but it doesn't support USB at all. So the only computers in the room it would work on are this one up here and the one back there, the one in front of John, the one Alex is usually sitting at. Or no, that is the one that you're at. Yeah, that was the one in front of it. Anyway, yeah, that's got a PS2 keyboard on it. The keyboards in this room are slowly failing, and so we're pulling out older keyboards from the room back there as they have problems like the spacebar button sticking. Anyway, actually the one over here might have, yes. Well, this is the PS2 one, the big one. Anyway, so it's nice if software supports modern keyboards for this kind of thing. So we'll have to learn how to do that. Okay, I'll show you the project description here and we'll open up today's notes too. Okay. So the project this is due, it's into November, which is a different month than this one. But it's kind of early in the month of November, so don't wait until it's November to start the project and then have trouble. This tends to be one of the more problematic projects. So the keylogger function is a loadable kernel module, so you insert it like usual, and once it's in the kernel, it starts working. And it'll track the last 15 characters typed and check to see if they meet common password rules. So that's kind of more of a CS111 or CS312 kind of challenge, but you have to take care of it in kernel space, which is not that different. And so then once you figure out that it meets those rules, then you need to record it. And so you'll have to actually record these things in some kernel memory somewhere so that when your file/proc is accessed, you can provide these. Okay, you can incorporate time if you want to. Generally, people do type passwords faster than other things because they're used to typing the password. And so it gives you a greater sense of rhythm with the password. I mentioned before, though, how if you push it too hard, then you always type your password wrong and everything else right, which is a good thing to avoid. Anyway, people actually have a little bit higher cadence on the password. Okay, so then details. We added an interrupt for interrupt handler 1 before, but as noted, that only really affects people with old keyboards. And so we can do better than that. There's a kind of an interesting article here. I left the link in here, even though it's slightly obsolete. Apparently, it's got a problem with their HTTPS these days. We'll go do. Oh, it doesn't exist anymore?
Oh, wow.
Oh, that's too bad.
Good link.
Okay, we'll have to pull that out of the article. So there's or find where it is these days somewhere else. Okay, well anyway, there used to be an interesting article here that I found an interesting read, but it mostly gives kind of obsolete methods. And so these days you want to support USB keyboards. Okay, so it has this note here, refer to the demo in class from October 10th. Hey, that's today. So we'll go over that one in a minute. And there's notes here, use /proc, we've been talking about that. Okay, all the rest of that stuff is pretty normal. Okay, so let's take a look at that demo then from today. Okay, it's in a soft run. You can get to it online too. I'm just going to do this because it's kind of easier. abd.c, I think that's what I called it. Okay. So this is it. It's really a pretty short little demo. It has this keyboard notifier function, and we actually register a keyboard notifier. And so essentially we're attaching a callback here that's going to get called whenever any action happens on the keyboard. So an action happens on the keyboard, our function kb notifier fn will run. And it does a print k here, puts into the kernel log a few details about what has just happened. So let's go ahead and try building it and see what it does. Okay. Okay, it built. Okay. Okay, it's in. So when we run dmessage here to see what's appeared in our kernel log, we can see that there's actually quite a few keys that have been pressed. And so if we push the up arrow and then enter, we'll run the whole thing again. And so let's do the up arrow enter about a few times. Okay, so we should have kind of a repeating pattern here. So I just did the same thing a bunch of times in a row. We've got key 28, and we've got key 61,953. Then we've got another event for key 61,953. And then we have key 28 again. Then we have another couple events for key 61,953. Then we have key 103. And so you see there's a few events for each of these things. What's not shown here is that there's an up and down event, and you can actually tell them apart. And this will happen for the keyboard over here too. So if I type something on this USB keyboard, let's say I write A. Oh, is it not plugged in? That would be the problem.
Huh.
You just lost something.
You changed screens.
Yeah, I see that. Okay. There you go. Okay, so if I write something here, there we go. So when I was doing all those A's, you saw key 30, key 30, key 30, key 30, key 30, key 30, key 30. And then eventually we have that same kind of pattern with key 28 and key 103. So it works perfectly fine, regardless of which one we want. What's that?
And a bunch of 64,353.
Yeah, a lot of 60.
What is that?
And 62,979.
I mean, if all you're hitting was A, what?
Okay, so this reports any activity on the keyboard whatsoever. That includes down, and it includes up, and it includes any change of status like shift keys and that kind of stuff. And so you end up getting quite a few things in here. It'll take a little doing to figure it out. So let's go through this code 1 minute at a time. And maybe I'll remove this module.
So the press
Okay.
B, key 30, and then the release was the big number?
Yeah, but then there's extra stuff in there too. Okay, so the keyboard, so module here, it starts with the module init function is init right here, and then we've got exit, which is a cleanup right there. So here we've got this, the first line of our keyboard notifier thing, nv.notifier_call. Okay, so looking at the pieces from this, nv is right up here. So nv's type is a struct notifier block. So that's what we got for NB. Okay, so let's take a look at what a struct notifier block is. I'll put this in a separate window here. Source 4.9. Okay, so it's probably an include and probably a Linux. They just need R on the IR. Okay. So lots of mentions of this struct notifier block, but it looks like notifier.h is probably what we're after, where you have a struct notifier block opening bracket there. Notifier.h. Okay. Okay. And lots of references to notifier. Okay. So this up here declares that we're going to have a struct notifier block. but it doesn't actually define the notifier block. That'll be a little bit later. We saw that there's a notifier block followed by a opening brace in here. So there you go. Struct notifier block. Okay, so it's got a notifier FNT, notifier call, and it's got a next, and it's got a priority. So if you look over at ours, our struct notifier block, the only member we're actually populating here is the notifier underscore call. And so notifier call is of type notifier FNT. Okay. So we take a notifier block, we fill out this one member, and then we pass the address of, see ampersand, address of our global variable notifier block up to this register keyboard notifier. Okay, so let's look at what a notifier FNT is. I suspect most of you can guess already on this. Okay, so here's a good type def for you. We've type defed one thing is another here. So a notifier FNT is a pointer to a function that returns an int and takes as parameters a struct notifier block, an unsigned long action, and a void star data. So those three things are the parameters. So if we look over here, since this demo works, we can guess that probably that's going to be the profile of this KB notifier FN here. And indeed it is. It returns an integer, takes a struct notifier block, takes an unsigned long action, takes a void star data. Okay. So it matches the correct profile for this notifier block. Notifier blocks are used for more things than just the keyboard. It's kind of a profile for something that's going to need to be notified when something in particular happens. So in this case, we're setting up that function to get called when this when the key is pressed. Okay, so then we got the register keyboard notifier function, and we won't go find that. I think you can probably tell what it does easy enough. We won't go down that particular rabbit trail right now. Okay, so then up here in this KB notifier FN, so now that we've put the address of this function into our struct notifier block, given the address of our notifier block to register keyboard notifier, when a key gets pressed, this function is going to get run. Okay, so first parameter here is we have a struct notifier block. And this is the address of a struct notifier block. And I believe this is just our notifier block. You might look at this and be like, why in the world do we need our own notifier block that's in fact already called NP, since it's a global variable there, pointed in as our, brought in here as our struct notifier block. The reason is if you use the same function here, it's supposed to be this KB notifier FN for notifications for a few different things. Say we registered it to be notified for the mouse as well, and it was just like our notifier FN or something like that. We could do that, and then we could tell by which struct notifier block we were given which notifier we were exactly. So it can get used for that kind of thing. Okay, so then we have this unsigned long action. And action isn't actually used anywhere in this function. But it gives us a value for action. We can print it out if we want to. But all of our data is actually coming out in this void star data. Action equals %sign D. Okay, there we go. Okay, so then we got this void star data. And so void star, generic memory address, we got the memory address of a something. And it happens that this is the address of a struct keyboard notifier param. So let's take a look at what's in a struct keyboard notifier param, okay? Okay, so we search for that everywhere. See in keyboard.h, this line right here, struct keyboard notifier param, opening brace. Okay. So there is a struct keyboard notifier param, and it's got a struct VC data, and so this is the way you could access that keyboard where the press was done. We did a bunch of looking at the VC and following that particular trail with the blink module. We don't necessarily have to do that for this one, so we won't do that. Okay, it's got an int down. And there's this funny comment here, pressure of the key. Keyboards are by and large not pressure sensitive.
Right.
Don't think of this as something that will unlock the hidden functionality where when you press keys really hard, it makes some capitals or something like that. There's just not hardware support for it. But this lets you know if the key was pushed down or not down. So it's kind of a down versus up sort of switch. I don't know why the comment is here exactly. It could be that the idea was maybe on some keyboards, instead of just 2 states, since you got an integer, you can have 4 billion states. You can have like a pressure specification or something like that, which could be cool. There's tablets of pressure sensitivity. Got a couple of those around. Anyway, so we got down, we got shift, current shift mask. This gives you an indication of whether the shift key is pressed or not pressed. Whether the shift key is pressed or not pressed is important because if it's been pressed, then you'll get a capital or a different letter off certain things. It's good to know. LED state. What's the state of the LEDs on the key? So this will let you know if the num lock or caps lock is on, which also changes which key it means. Keyboards seem really simple until you start thinking about it. And then if you think about some button, what does the A key on a keyboard do? Well, it gives you an A, but is that a capital or a lowercase a? It depends on if the left shift is down or the right shift is down or caps lock is on. And if caps lock is on, then shift brings it back to the other status and gives you a lowercase letter. And so you can see how the logic starts to get a little bit more convoluted. Anyway, so you have the state there to work with, and then you have the value. And that's the key code. And there's some notes about what exactly is it. Is it a symbol? Is it a key code? Is it a Unicode value? You notice when I was pushing A, I think I was getting like 30 or something. And that's not the ASCII value for A. And that's not even ASCII value for A in hex. So you're getting a key code. And so the key code, there's a mapping here between key codes and actual key values. And so that'll have to be discovered on here. Okay. The thing about the key map. So you can have different key maps. There's a pattern out there called Dvorak, and there's actually a number of others too. Dvorak is the most popular, well-known. Okay, so here's a Dvorak key layout. If you look at it, it'll look unfamiliar. You probably use the QWERTY, unless you type Dvorak natively, in which case I should quit assuming that it doesn't look normal. Okay, so the Dvorak keyboard has all your keys in different spots. And they make actual ones. It's a Dvorak keyboard.
I've known of them, but never actually used one.
Yeah, so here's a Dvorak key. That's not a Dvorak keyboard. That's a QWERTY keyboard. So there's the layout. Well, anyway, we don't spend forever looking for a picture of a physical one. They have them. Maybe you just have to take my word.
Oh, there was one. There's that bent one.
Is it Dvorak?
I think so.
AC, yeah, that's Dvorak. That is. Cool. Okay, so there's those. And you could actually make one if you wanted to. The keycaps on these things are interchangeable. So if you wanted to take, the F12 keycap off and put it somewhere else, you could do that. They come right off. I have a ritual occasionally, which I need to do again, where I take all the keycaps off and then I put them in an ultrasonic cleaner. And then once they're all clean, I put them back on a keyboard without looking. And then I check to see how close I was looking at a different keyboard. Anyway.
Remember the spots.
Yeah. Well, it is irritating if I mix up something like home and end, and I don't notice.
Nina got really annoyed by the end. Like,
That's right. I forgot that I'd left that. And I didn't notice because I don't look when I type.
yeah.
Yeah, okay, so the key map. So you have a hardware device like the keyboard, and it's got lettering on it that's really decorative for the user because you can just take these things off, F1 and F2. Where do they go? They should go where A and B are. So since the keycaps don't necessarily have to be in any particular spot, you can actually just move them around. Okay, and now I'm doing stuff on the other monitor that you can't see. But I should quit doing stuff on the other monitor where you can't see it. Okay, monitor that one. Okay, the kernel has to contain some kind of key map to straighten all this stuff out. And so if you wanted to have a Dvorak keyboard, all you have to do is let the kernel know that you have a different key map, and then all the keys can be mapped to different spots. This is also true of international keyboards. So the funny thing about keyboards, they have this weird tie-in to the English language since they came about, I don't know, in English-speaking areas. And so we kind of put them together, assuming that this is all the letters in the entire world. But this is not all the letters in the world. So it's occasionally frustrating. If you're trying to type in a different language, like it's missing the N with the tilde over it. That's not a key that we have. But you can substitute a key map, you know. If you're like, okay, well, I want to have the N with the tilde over it as a key. And the fact is, I hardly ever use the, say, regular accent tilde key. You know, you could actually map it and say, okay, this is going to be my new key. And you can take a Sharpie and write it on your keyboard. And then it's, you know, changed, right? All fixed. So anyway, keyboard maps can be modified. Keyboard maps are not exactly the same from country to country. It's sometimes a frustration for people coming to this country that their favorite letters are not on the keyboard. Okay. So all that to say, the keyboard doesn't produce ASCII values natively. Okay. So when you make one of these, so when you have something like an action, you have to map that to the right thing. Okay. We did value, LED state, and width. We did not put in the down. Whether or not it's down. Whether it's down. Okay. Shift map is that. Okay. Somebody shift map. Okay, and then percent sign P. Okay. Okay, so KP down. Got it. Okay, let's go ahead and make this thing again. There's a warning there. Percent sign D expects a
You didn't.
hint.
Yeah, you didn't add anything
For action. That'll still probably warn us because it's a long unsigned hint. W. Correct one. Okay. Okay, so we have all this stuff. So action. Flips
One and
between a
four.
1 and a 4.
There's a 5 in there too.
Is there 5?
Oh,
Oh, yeah, there's 5. You're right. 5. There's 4 right there. Now, I noticed something convenient. All of these super high things that aren't necessarily related to pressing a key that we care about is giving us an action like 4 or something
5.
like that, or
Yeah.
5. And if we get an action 1, it's a key with a low value code that's either down, like in this case, or it's up, like in that case. And so when figuring out which keys are pressed, like if you just wanted to figure out which letter key is pressed and you don't care about when it's up or anything else, you can actually filter this out based on the action and whether it's down or not. You can also look for a range kind of thing for this number right here. So it's fairly straightforward to just look at it and figure out the pattern. Everybody in CS likes looking at patterns and figuring them out, right? I mean, we're all the type of person where if we see a brick wall, we stare at it until we figure out what modifications were done on a building. Maybe not.
And it's easy to pick out a flaw in the pattern too. Like, oh, that brick's cracked. And you might be looking at 1,000 bricks in one little area, and you're like, hey, that one.
Yeah. Some people are better than me at it. My sister-in-law can spot a 4-leaf clover in like a field of grass. It's like look around and be like, there. I can't see him. Anyway, so there's a definite pattern going on here. Okay, so you can pull out the keys by key code and then come up with a mapping to actual text and characters.
Question.
Yeah.
Where's the map held?
The map. Okay. So there's going to be a couple of them. Now, if you look at this unsigned short, you got this reference to key maps here and a plain map. And these get populated, but somewhere else. Varies depending on which version. But you can find it from there if you start with these keywords. Won't take you too long at all. Okay, so that's that part. Okay, so let's take this and modify it further a little bit. Okay. Okay, so we got the keyboard thing here. It's pulling this thing out, it's giving us all these actions and whatnot. So from this, we should be able to squirrel things away and provide them later. That should be good. And we could actually take this and bring it back to our speed, but just change it into letters, kind of like we did last time. So last time what we did, okay, we did an interrupt speed test. That was an KB test. Let's see. Okay. So we counted how many calls per second here, and yeah, it worked pretty good. Okay, so for this one, we'll just go ahead and take the same kind of concept and support USB keyboard. So KB test.c to USB test.c. There we go. And then a copy. Okay. Then we'll go ahead and grab our keyboard.c and put that into USB test. Okay. Okay. So last time, we got these two different ones here. Let's go ahead and pull out a lot of this block here. I think KBD demo is a way better module name than netmon or whatever we had before. So that'd be good. Last time we were doing this kind of T count based on the IRQ handler. We don't want an IRQ handler anymore. The read proc is perfectly fine from last time, so that's good. Start things. We have a different init now. So with the exception of the proc create, we'll just go ahead and take our new one. Same thing here. Okay, so then we got the stuff from our new demo right down here. A few things again are going to be redundant. So we have the read proc from our old one. We're going to need the notifier block to keep all this stuff organized. It's important. It's good to keep these things organized. The other read is much better than that read. The file operations. We got two versions here. Keep the top one. Then we got our keyboard notifier functions. That's where we're going to have to say something about tcount. If we put tcount plus plus, we'll go all keyboard related actions. You better say something like if action equals 1 and then let's say the state KP down. So say that that's true. Then we can add to the tcount. There we go. So then we want to add this the proc create right there. Our proc fops is called PFO above, and so it would be good if it said the same thing here. And then we got the unregister one, same thing. We got two versions of this. Looks like ours are called init and cleanup, so we don't want that one. If I can type today. All that extra space. There we go. Okay, so this should give us something kind of like last time's demo, except it should support USB keys, and it should only tell us when a key is pressed down. And so it should give us a lot more accurate count. It'll actually give us a lower number. I suppose that's fine. Okay, and so let's go ahead and make that. See if it works. Okay, does not build yet. Dereferencing pointer to incomplete type struct keyboard notifier param. Okay. If we look at kbd.c, it's going to have an include up here that's important. It's probably that one right there, Linux keyboard.h. You can see it's missing up there. What do you think about include files? Is that oftentimes one include file includes a half dozen other include files. And so it's sometimes hard to tell which ones you're missing just by looking at the top, because you might have said one that includes others. Or if you have this sort of situation where you've got include file A and include file B, and include file A includes file C, which you needed, and you switch from A to B, then it'll say that C is no longer included, because it's not, even though it's not obvious. Okay, anyway. Go ahead and take out our first one. Okay. So, we have this function in here, read. It's compiled into, I thought it was compiled into A.out. Readlen -1. That's, no, it's got the wrong file name in it. Because it's called like KBD test or something like that. It's called KBD_demo. And if we look at our read test one here, it's expected to be called netmon. That's what it was. Okay. There we go. Okay, so then if we start this thing in a loop, and okay, there that goes. We'll go ahead and split the screen here, and so then we can just start writing. Anyway, so if I stop it, drops back off. Cool. Got a typing rate thing. Okay, I don't need to say this, but for some reason my daughter always asks for stories at night, and my stories are always equivalently weird to that. Anyway.
So, I think it just count when you press it down, no? It doesn't count when you put it up again?
Correct?
Okay.
Yeah, that one does just one way now. Okay, so once that all works, project 3 should fall before you, hopefully. Okay, now the module list and LSMod. So, let's talk about rootkits real quick too. Okay, when you LSMod, you can see what modules are currently in the system. And so, if we, I thought I had a question back there. We look for, it's not called USB, it's called KBD test. Okay. I thought it was called USB test. Oh, we're on a software. Well, that would be why. It's not on a software. Yeah.
How do you get away with having a program a keylogger when the school rules say we can't do that?
Do they?
Yeah, there was a thing a few years, you just went over it yesterday, that like a few years ago, somebody plugged a keylogger in
Well, yeah, they did.
things and,
Yeah, there's like been a hardware keylogger up here.
yeah, in the school rules, it says that like no keyloggers allowed at school at all.
Oh, does it?
Yeah.
Didn't realize it said that. I know it said that you weren't allowed to use them to steal people's passwords.
Yeah.
I
You're
read
playing,
Project 3
it's
over
okay,
here.
but we're not using it.
Well, no, I'm wondering if, how we're getting around it, because if we just don't tell anybody, I guess.
What's it actually say?
I mean, we're already using virtual machines for Apple, and we have to go to.
That's where did you find it?
Nina was just going over it yesterday.
Oh,
She was saying that like we weren't supposed to have keyloggers at all, whether physical or programs.
I haven't seen that one anywhere. I wonder if you saw it.
I think she was just talking about the example of a couple of years ago.
Yeah.
Or something,
Well, yeah.
but I don't know.
You might just be discouraging malicious behavior.
Well, yeah, that other example a few years ago, the takeaway was that malicious behavior involving keyloggers was not allowed. I don't know. I'm running this one for this is the 4th time we've done this class, and it hasn't been a problem.
Okay. I should look, like if that never came up, I wouldn't know about this, I would have asked.
Right.
Just wanted to, sure.
Yeah, it's a good question. It's interesting. I should make sure that we're not actually violating some kind of policy here. I don't know of one.
We can all work on it at home, I guess, and just like go to school computers and that.
There is a computer use policy. It actually says you can't have any video games on it too. No, seriously, no. The reason that I know that one's not a big deal is the State Board of Education is pushing a game development program over on CITBT. And so I know they don't know about it. but technically, our gaming club is very not allowed. So,
Great.
yeah, well, yeah. Well, it's like kind of a gray area. Okay. Computer, that's all I wanted. Yeah. Computer use policy. There's a personal one and a surplus one. Okay. So, how long is it? Pretty short. It probably just refers to a different policy, though. This is users of Idaho's personal computers, and you can't load, download, or distribute pirated software, may not load or download entertainment software and games, or play games from state-owned computers. Complete Idaho's policy is here. That's the surplus one. This one's the slightly longer one. I read through it once in order to see what was actually in the thing. Looking for, here, I'll look at keylogger. The word keylogger is not mentioned. Not sure that I see anything exactly related to it. The pirated software thing comes through a few times. Entertainment software and games comes through a few times. The state may inspect everything. I don't know.
Looks like they're just all about the whole no piracy, no games.
Yeah. The surplus computer one is the one that I've never liked. It's got somewhere in it that prevents, it might not be here, it might actually be what we do in practice. I can't remember. I looked into this for a while, and
Yeah, you guys got rid of a bunch of computers a while back, right?
yeah, and I've always wanted to be able to sell them off for peanuts, but that's not been allowed.
What does the campus actually do with them?
Recycles them.
What, so like the old lab computers here just like went to the recycling center?
No, they're sitting in a closet, because they're just going to get recycled anyway. Maybe we'll need them for something,
So they'll be sitting there 10 years from now.
probably. Anyway, I guess the guideline's not actually in that one for the recycling thing. Anyway, oh yeah, there's also the appropriate use for technology. It could be in that one. Okay. Okay. No word keylogger. So this one's kind of longish. Oh, this is the one that bans hacking on here. Use of the college's information technology resources to attempt unauthorized use or interference. No, that's bad. Modification or reconfiguration of the software, data, or hardware of the college's information technology resource without appropriate authorization or permission. Creating, installing, executing, or distributing malicious code. That includes viruses, worms, and spyware. Theoretically, my computer science, my security demo, where I actually write a virus. Cover that one. I write a surreptitiously destructive program. Hacking, attempting to gain access to unauthorized areas into college computers, and copyright infringement, of course. Using electronic equipment attached to college resources to capture data packets, which the network class could sort of run afoul of slightly since we use Wireshark. Just doing here. Sending abusive, threatening, or harassing materials is certainly not allowed. Knowingly interfering with security mechanisms or integrity of the college's information technology resources. I've occasionally hacked past MAC address blocks in here, which probably technically violates that. Connecting electronic devices, which is routers, hubs, computer systems, wireless access points to the college network that are not approved. Potentially physically or damaging things, of course, is not allowed, and then removing any computer component or equipment from LCSC's campus without prior approval of the IT department or the relevant division representative. Gaming club, I tried to do that recently.
Well, I mean, there are forms that can be filled out to do it. It's just we figured that it wasn't.
Well, you're running into an insurance problem.
Yeah.
Yeah. Anyway, you could take one of these things and pull it far enough in to talk about keyloggers probably.
I mean, technically the policy that is the one about the spyware, because that's what keyloggers are. They're spyware.
Right, although a lot of times with the spyware, it's assumed that the spyware is something that gets distributed onto somebody's computer to spy on them, which is rather different than if you're writing spyware for your own computer to spy on yourself. The spying nature of it is sort of lost then. Yeah, I doubt that it's really a problem looking through the policies, again, at least in the context of this class. I wouldn't recommend using it to steal somebody's password.
See, as long as it's on the resources that we're approved to use it on and we don't put it anywhere else, then there's no infringement.
Right.
Yeah. You can
Because
geek
we
your own
literally,
computer all you want.
well, it's literally permission from the instructor of a class doing it for educational purposes.
Right. One other thing I should point out here, the IT department finally got tired of us being weird and put us off onto our own network. And so in doing that, they kind of gave us permission to do what we like. Not kind of, they said we should do what we like. And as long as there's not a problem that, blows up on them about it, it's fine. And so that means we have to make sure that there's not, if we're found with pirated software in the lab, for example, that could cause an actual problem. But other than that, we can do our own DNS servers and network traffic monitoring and all that kind of stuff in here, separated from the rest of the college network. So it's just the same thing should apply to keyloggers. Now in this one, I would recommend don't leave it running when you leave, because other people might sit down at the computer and then, you capture your information, whether you intend to or not. Yeah, good question to raise. Good job. Okay. There's that, and then there's one other thing I was going to mention about it. Oh yeah, so the LS mod. And when you're in LS mod, we go here in LS mod, and let's say we use grepin here to find our actual module. Okay. I thought it was in this one, this one right here. Called test, USB test. There it is. Here. Oh, it's the top one. I just can't see it. Okay, so the USB test is still in this kernel here, and it shows up in the list of modules. So let's talk about spyware rootkits. This is a perfect introduction to the topic. Some time ago, I guess this is probably 10 or 15 years now, Sony got in some trouble because they wanted to prevent people from copying the music off of their CDs. And so what they did is when you put a CD into a CD-ROM drive on a Windows computer, it looks for an auto-run file on the CD. And so shortly after the drive closes, if the operating system finds this file, I believe it's called autorun.inf, it will go ahead and run software directly from the CD. This is intended as a convenience for non-technical users who don't know what to do once the CD's in the drive. And so after they put the CD in the drive, say an install program can show up, or the CD player can automatically start, or something like that. So the software that was on Sony's CD actually exploited a vulnerability and installed a rootkit into the kernel. So then the rootkit would look for attempts to copy the CD, and if that happened, it would stop it in order to prevent the user from copying it. Unfortunately, the rootkit actually had a vulnerability that made the computer vulnerable to remote access. So that's part of what caused the trouble for them. It proved to be unpopular. And it only affected people that had auto-run on. If you don't like that behavior on Windows, you can turn the feature off, and then it will ignore the CD until you tell it what you want to have done with it.
That's still pretty malicious for them to be, installing a rootkit on your computer.
Right, right. So the reason people are concerned about rootkits is the only evidence that this thing's in the kernel is, first of all, there's a note in this list on this kernel module USB test, and secondly, there's the proc file that we use to interface with it. However, both of these can be avoided with care. These modules are just stored in a list. The list is tracked in the kernel and reproduced when you run the lsmod command. However, if you're putting code into the kernel, you can edit the list and you can edit out your own entry. which would prevent it from showing up in this particular list. The other thing you can do is give it an innocuous name.
So it just kind of blends into the mess.
Right. That would work fine too. Editing it out though is really not all that difficult, and would hide it from this particular list. Then the other thing we've got is the file in /proc. How many of you reviewed your /proc directory this morning to make sure there weren't any entries that you didn't recognize? Yeah, I didn't either. So it's easy to hide something in there, but that's not the only way to do it, not by far. The first time I ran this project, I think it was the second time, I can't remember. One student decided that the proc file was just not good enough for a good key logging system. So what he did is he wrote a little web server, or not a web server, just a regular server. He wrote a server on a soft drive that would have a port open waiting. And so then periodically, the computer would actually take the whole list of passwords and send them off to his server on a soft drive. So you could see remotely what had happened. And so in that case, you don't need a file in /proc. He had one that was there just to fulfill the assignment criteria. He was like, oh yeah, so I left this here. That way I get 100%. It's kind of like, hey, you get 100% anyway. It worked pretty good. Now that would give you just a little bit of unexpected network traffic. And so if you diligently inspect all of the network packets leaving your computer, you would notice. But again, we did that this morning. So it's actually very easy to hide a rootkit. It's also harder for software to find. It doesn't have to have a file anywhere once it's in the kernel. If we delete this module from here, it's really not a big deal. It'll continue ticking along just fine until the computer's rebooted. It does have to go somewhere, and so it could stay with the rest of the modules. If we trust that the computer won't be turned off abruptly, it can be written while the computer's shut down, although that is defeated if the user is playing with a power strip switch with their toe or something. We could pull it from somewhere else, but that requires a mechanism to do it. Or finally, we can compile it directly into the kernel and replace the operating system kernel with one that has it compiled in. And that would be very difficult to find, unless you reliably check to make sure your kernel hasn't changed. So there's a variety of ways one can do it. But the main problem is, once there's code inside the kernel, it's really underneath the whole permissions thing. It's not that it's running a super user privilege, it's the privilege no longer applies to it. That's an entirely different level. You see we have different levels of privilege to access offices in this building. The highest privilege level is referred to as janitorial, and then you can go into any office you please. But you still have to currently have permission and have keys, and the key has to not be out of date and all that kind of thing. So this is more equivalent to just you can walk through the door because it doesn't apply to you.
Sounds like IT.
Yeah, they have a similar privilege level. Okay, so that's rootkits briefly. Now, usually to get a rootkit installed, you have to coerce the user to put it into the kernel in some way. And so you need to do something. And
that's what Trojans are for.
Yeah, I mean, it varies exactly what you need to do. I mean, sometimes they're bribable. If you say, you get 100 banana bucks, a lot of users will take you up on that. They won't necessarily care what a banana buck is. Anyway, so that can be done. This is one of the reasons that Microsoft has had so much trouble putting a robust permissions model into Windows, is that all the users say, wait a minute, we have to enter our password for all this stuff? What a hassle. And so
the thing that Linux users have been doing for ever.
Yeah. So then they just are trained to type the password whenever the box presents it. It actually enables a really good phishing opportunity. Anyway. Okay. So rootkits. Okay. So we're making a kernel module, and it goes and tracks all that stuff, and that's good. Talk about caps lock, talk about key codes, and /proc. I think we're pretty well good on that stuff. So any more questions on project 3?
Oh, that'll be coming.
That'll be coming.
Wait
Okay.
until we start.
Okay. Okay. So let's talk about synchronization. I thought I was going to end up using up all the time on this thing, and we got 20 minutes, and so we might as well.
Even with the big old diversion in the policy.
Yeah, we're like way ahead. Okay. I never asked IT if I could SSH into my machine in my office. Okay. They actually know about it though.
And
Okay.
I would gather they probably don't care.
They don't care. They only really care if there's problems that go on. Okay, this is the occasional random irrelevant note. But let's start talking about synchronization and concurrency, because that's kind of the next next issue that we'll go over. So this is coming from chapter 9, I think, in the book. Okay, so with concurrency and multiple processes running at the exact same time, it's possible to have multiple things happen at the same time, and that can cause all kinds of chaos. And so it has to be expected that the kernel can be invoked in multiple places at the same time. And this has been true even before we had multi-core CPUs. For example, if you had some kernel code that was running, it could be interrupted by an actual interrupt. So then the interrupt begins running. Normally with an interrupt handler, you actually disable interrupts for a moment so that the interrupt handler won't be itself interrupted. But when the interrupt handler is running, it means that there's some piece of code that was running, and now it's been unexpectedly stopped in the middle, and now something different is running. So the thing that was unexpectedly stopped is in the middle of some important operation, and the thing that's currently running changes something related to that, you can have a problem. So if you take a linked list usually have nodes, and you have like A points to B, which points to C, and so on. And so the kernel linked lists work the same way. But suppose you're busy inserting an item E, and you're going to insert it after A. So the final solution that you want here is going to have A point to B, point to E, excuse me, which points to C. And so if you're just running this whole thing single-threaded, it doesn't really matter what you do. So suppose you say, okay, A is going to be linked to E, not B. And then E, I guess it has to be linked to B, actually, in order to not delete B. E is going to be linked to B after that. Well, that's all fine and good. But if you're in this state, and the other process decides to go traverse the linked list, it's going to have a problem.
I remember dealing with this.
Yeah. If you delete something, suppose we want to delete this C right here. We're going to take C out. Okay. So when C is being deleted, you'll have this situation. And you can fix this situation by just adding this link here. But supposing you haven't added it yet, and C is already in the process of going away, then again, you can have a problem. Synchronization in data structures is quite important, and there's a lot of other areas where it'll come into play as well. The thing you probably remember is maybe game development class. We did this in game engine design, and we had a list of game entities, and you could delete one. But if you deleted one, well, the drawing system was busy running through them, then it would have unexpected effects. And it's kind of manifested as the game engine would generally just sort of be flaky and crabby at times. And until we finally fixed it. It was complicated enough, in fact, it didn't show up immediately. Okay, so the usual way to protect this is a few different structures, and they're mostly available in the kernel. There's locks available. I demoed this with pthreads in the past, and that might be a decent idea again. With a lock, a mutex is an example of a lock. There's a few different types of locks. Okay, so mutex stands for mutual exclusion device, and you can lock it and unlock it. So if we look at pthread mutex, unlock, mutex lock, pthread lock. Denied. Okay, pthread, it's lock. There we go. None of those are right. That was lock and unlock. But we look for lock. There's the pthread ones. Really, I don't use these often enough to immediately remember what they are. Oh, I bet they're in here. Oh yeah, pthread, mutex, lock, and unlock. Sure. Try this.
You started talking about mutex and got Alex all excited.
There we go. Hold on. Oh, was Alex watching remotely? Okay. I'm glad he's excited about mutexes. Okay, so for some reason, the man page was not on the machine in the room, and so that's why I could not guess it right to save my life. Okay, so the pthread mutex lock, the pthread mutex system, allows you to have this entity called a mutex, mutual exclusion device, like it says there. I don't know why we picked 3 and 2 for the number of capitals. Maybe it sounds better than if we take MU and EXC. Anyway, once we have one of these, we can protect shared structures. So we can lock these things and unlock them. We can initialize a mutex when we're first starting. We can try to lock them. So the difference between lock and unlock. Let's talk about dining philosophers, just to get a problem on the board. Dining philosophers is kind of a fun problem because it shows how weird philosophers are. Okay, suppose you have a bunch of philosophers and they're sitting around a table. And so there's philosopher 1 and philosopher 2 and philosopher 3 and 4 and philosopher 5. Okay, and so they're all sitting. And each of them has a plate. And so they have food to eat. And they need to eat. So then between each pair of philosophers is a chopstick. Single chopstick. Okay, so in order to eat, each of the philosophers follows the following algorithm. Pick up right chopstick, and then pick up the left chopstick. Okay, and then you eat. So that's the plan. Each philosopher reaches out and picks up the right chopstick. Now, none of them can pick up the left chopstick because they're all holding. This one's picked up that. Yeah, they're all holding. Okay, so this instruction takes a long time. So they sit there waiting to pick up the left chopstick until they all starve. Okay. Now, I've seen this one stated once. I think somebody decided to westernize it, and they had a fork between each of them instead of a chopstick. But it didn't make it any less weird because they need 2 forks to eat. Anyway, so the way for the philosophers to survive is, if they pick up the right chopstick and they can't pick up the left chopstick, they should put the right one back down. And they have to be, to some extent, unsynchronized, because otherwise they'll just all sit there picking one up and putting it down all evening. And nobody will ever get to eat. But luckily, the timing normally doesn't happen quite that much in lockstep. And if you're concerned about it happening in lockstep, each of them could put it down and wait a random number of seconds before trying to pick it back up. And then whoever waits the least number of seconds will get to pick it up first, and hopefully they'll get the other one too, and then they'll get to eat, and then they'll put them down, and somebody else can take their dirty chopsticks and eat. The random back off, it's got a lot of precedent. For everybody that was in networks class, probably remembers it's part of Ethernet. 2 computers send a packet at the same time when they collide, then they just both each wait a random amount of time and then try again.
I was going to mention first.
Yeah. Okay. Yeah. Yeah. So that's the plan here. Okay. So if you wanted to implement an algorithm there where the philosophers survive, you could use try-lock. The difference is lock will wait until the lock is obtained, and there's not really a timeout. It just keeps on waiting. The try-lock will try to gain the lock on the resource, and if it can't, then it will actually go and let you program something else. You get back an error value from try-lock, so it returns this int here. And try-lock behaves identically to pthread mutex lock, except it does not block the calling thread if the mutex is already locked by another thread, or by the calling thread in the case of fast mutex. There's mutex types where it's possible to lock a thread, lock something and then end up waiting for your own lock. It's a little bit hard in reality. It's sort of like if you like lock the porta potty when you go inside and you like climb out the roof and then stand outside waiting for it to be unoccupied so you can go in. But you can do that with these things. Not a problem. So the tri-lock will return immediately with the error code "be busy" if the lock cannot immediately be obtained. Good behavior there. Okay, unlock unlocks it, and that's a sim. Okay, so there's these notes about fast mutexes, and so then there's a corresponding type that's not a fast mutex. So pthread mutex init up here can initialize a mutex, initialize the mutex object pointed to by mutex, which is a pthread mutex t. Okay, and so the pthread mutex t can be either set to a pthread mutex initializer, or a pthread recursive mutex initializer, or a pthread aircheck mutex initializer. Okay, and all of these things have slightly different behavior. Recursion on these things, it's defined somewhere in this page. I'll quit scrolling up and down, making everybody dizzy for a moment. A recursive lock versus a regular lock. So suppose that you actually are planning the sort of situation where you're going to go in the bathroom, lock the door, climb out the window, and come back and wait outside the door for yourself. If you do that, then what you might want is a recursive lock. And with a recursive lock, if you're trying to get a lock that you yourself hold, you're allowed to have the lock, and it usually increases the count of how many times it's locked. So it's sort of like if you go and unlock it, but then you like add a second lock to the door and lock both of them. And you can go around again and add a third lock to the door. And so eventually you can go and unlock each of these in a recursive manner. So having a recursive lock, though, requires that a count be kept, and so that makes it potentially slower. The other way to do one of these recursive locks is to say that if you acquire your own lock, it does not add to the count, and you only have to unlock it once. The problem there is that you might end up trying to unlock it multiple times. And this could be a problem if you have recursive code. Especially saying with recursive code, if it unlocks on the first time and you've gone through some call stack trip where you've got something locked on each frame, it'll get unlocked at the very, when it gets unlocked the first time, which could be a problem. So that's why it's usually counted in order to unlock at exactly the right time. Okay, so it's mentioned that there's these types. So each of these types can be initialized statically using the contents pthread mutex initializer for fast mutexes, which don't handle recursion. The pthread mutex recursive mutex initializer type for recursive ones, or you can have the error checking mutexes. Okay, so you got these. You can also destroy one of these. This is not like a more powerful unlock necessarily. Pthread mutex destroy destroys a mutex object, freeing the resources it might hold. Mutex must be unlocked on entrance. And it mentions in the Linux threads implementation, no resources are associated with mutex objects. Thus, pthread mutex destroy actually does nothing except checking that the mutex is unlocked. So now you know. Now, so the pthread mutex destroy won't automatically unlock it. And so you might look at that and be like, oh, that's great. If I can't unlock it, I'll just destroy it. The car burglar kind of thing, If we can't unlock it, we'll just destroy it. So that's not what this does.
Burn the porta potty down.
Right. Most of the time, these
That would
locks.
smell awful.
Yeah. Yeah. Most of the time, these locks are intended as more of a courtesy lock. If you think about a lock on a car, think about vehicle locks. I have a 1973 pickup, and it has a lock on the inside. And so I have a key, and it looks very much like the rest of the keys on my ring. It's actually two-sided, so you can put it in upside down. It doesn't have a whole lot of pins. So this goes into an electrical switch you turn. Now, the back of the switch has wires that come out, and in fact, it's completely exposed. If you go look under the dashboard, you can see all the wires. And all it does is control which wires are connected to which. So, in movies, the usual plot device was to pull out all the wires and connect them together. A friend of mine realized that actually it's way easier than that. The lock cylinder itself has a connector on the back of it that you can unplug. So if you wanted to steal a vehicle, you just bring the appropriate lock with you, unplug it from the one that's in the vehicle, and plug it into yours. And now you have the right key for your lock. So there's not a tremendous amount of security obtained by these. The actual thing that secured vehicles somewhat later, this started in about the 80s, steering wheel locks. And so with a steering column lock, it again has the electrical switches, and so you can start the car by pulling out the wires and connecting appropriate ones together. However, there's a purely mechanical lock involving moving metal blocks that prevents you from turning the steering wheel. And so although you're allowed to start the car and drive it away, you cannot steer it. This makes it more difficult to steer. To steal. You have to steal it somewhere where you can drive away in a straight line. Or whatever, the tires have to be turned.
Drive in circles.
That's when you just bring a drill.
Since
draw
then,
the
electronic locks have been added. I don't have any keys, so I can lock it with an
I've done
electronic
it.
locking module. But these days, the car has a cryptographic key that talks to between the car's computer and your key, and authenticates whether or not you should be allowed to start it, which makes stealing the car a little bit more of a hacking puzzle. Yes, like that. And in fact, does that have a physical key?
Yeah.
Okay.
Open the door.
But you don't have to normally use it. do you?
No.
You just sit in
There's
your
a
car
button
and push
for
the
it.
button and it goes?
Yeah.
Yeah.
Yours has proximity?
Yeah.
That's nice.
So it becomes entirely an electronics puzzle. I've only ever driven a car like that once. I borrowed my brother's, and it was actually very nice.
So there's like no ignition at all in the car.
Yeah.
Can somebody start your car if you're just standing right next to it?
Theoretically,
it
yes,
does not have a
but
start, no.
No, but like if you're standing next to it with the key in your pocket.
The key has to be inside the car. The fob has to be inside the car.
Okay.
It's not when you're outside the car, inside the car.
Right, there used to be a thing where like if you're just standing next to it, proximity wasn't like super good, so somebody could just turn it on from the outside.
And like if I'm in the car, the
Actually,
door's
that's still
locked, somebody
possible
can't
with
just
OnStar.
push the button and unlock the doors. If there's a key fob in the car, so you can't unlock the doors from the outside.
And the location accuracy is pretty good on those, although I imagine that if you had, say, a convertible and you duct taped it to the top of the cover, it might still work.
Break into somebody's car, call OnStar.
Yeah.
Hey, I forgot my key. Can you start this up for me?
Yeah, that's
Yeah.
possible.
Oh, but the thing about talking about locks here. So with security, we're looking for a lock more like the 80s and up sorts of styles, where you either have a mechanical lock that prevents you from steering or an electronic mechanism where the computer will refuse to actually release any fuel to the injectors or crank over the engine or anything until it's, contacted the right cryptographic token. Most of the parallel processing type locks are more like the 70s and earlier style lock. So you can hack your way around them. That doesn't mean you should. So, it's very much like, the locks on bathroom doors usually can be unlocked quite easily. I was at the dentist the other day, and they have a problem with their door where if it's open too far, the button on the lock gets pressed against the wall. And then if it's subsequently closed, it's locked with nobody inside. And so if somebody goes and tries the door or knocks on it or something and goes away, usually they just come over and unlock the door and there's nobody inside it because the door has been locked unintentionally. Okay, so that sort of thing is usually possible, but it usually indicates some sort of bug in the code that ought to be corrected. In this case, they need it's a rare and expensive device called a doorstop. And so usually this situation, if you're looking at trying to hack your way around one of these, it means that you need the programming equivalent of a doorstop somewhere. So you should figure out where it goes and add it. Okay. So that's the basic introduction to this stuff. We'll talk about it a bit more. I'll show you an actual example of deadlock. The Dining Philosophers is a case of deadlock here. If each of them was holding one chopstick and they're all busy starting, that's deadlock. Deadlock is it's straightforward to avoid. It's just that the more complicated situation you have, the closer it gets. The other thing about the synchronization is you want to avoid locking resources you don't need. So if the last philosopher to finish just puts both chopsticks in two different pockets, because of course he would, and walks away, without releasing your chopsticks, then that causes a problem for the rest of them. So you generally want to lock something for the least amount of time you can actually lock it. There used to be a mechanism in Linux up through version 2.4 that was called the big kernel lock, and it locked everything, gave you exclusive access to the entire kernel. That was excessive in most situations. And so it had a detrimental effect on multi-threaded performance, and eventually it was removed in version 2.5. 2.5 was a development tree. Nobody ran 2.5. I ran 2.5 for a while, but nobody ran 2.5. And so then 2.6 was the next release tree, and 2.6 was free of the big kernel lock. Anyway, so there you go. Okay. So one thing you can have with the locks that decreases performance, imagine for a moment that you've got a computer. Let's call it the Cray XMT. And it's got 128 processors that each run 128 threads. And they are adding up an array. And they've each been assigned a block. And the sum is stored somewhere. And so each of them locks the sum that they've reached so far, adds to it, and then unlocks it. They refer to this as a hotspot, because then you've got 128 squared processes attempting to change the same value at once. It won't cause a programming bug since it's been carefully locked, but it will limit performance to how quickly this piece of memory can be locked, adjusted, and unlocked. I programmed for the Cray XMT for a little while, and when I was at WSU. Anyway, yes, and that was their term. I haven't heard that term much anywhere else, but they use that term all the time in-house. Maybe it's become popular. Okay, in order to, and finally, to obtain these locks, you have to have hardware support for them. The reason is a test and set problem. If you're going to have a lock, say the lock is implemented as a binary value. It's true or false. So you check to see if it's locked, and it's not locked. So you lock it. But suppose between when you checked it and when you locked it, somebody else checked it, and then they go lock it. See where there's a problem? And so the hardware normally includes support for a test and set operation, which tests and sets without any kind of interruption since it's one hardware operation. So that's test and set. And so test and set can return two possible things. Either A, yes, here was the value and we set it for you, locked, or here was the value and no, you can't set it. Okay. I think that's it for now. So we'll see you again next week.
Yeah, what made me think of the whole network sharing thing with Johnny Philosopher.